The question that we'd like to ask right now is, how does a router know where to send a packet? After all, if I am here in the Portland area, Vancouver area, and I want to send a packet out to somewhere in New York, how does the router know what direction to send it? How come it doesn't end up in India somewhere or in Canada somewhere? Well, the answer is it uses something called a routing table. So, oh, not that kind of routing table. There, this kind of routing table. So if you look down here, these are the routes in this particular router's routing table. Now, we're going to take a closer look at this as we go along, but first of all, I want to ask another question. How do those routes get in the routing table? And it turns out there are 3 ways that that can happen. They can be directly connected networks, or they can be statically entered, that is to say, manually entered by an administrator, or they can be dynamically learned through a routing protocol. And we're going to be learning about routing protocols this week. Let's take a brief look at all 3 of these. The first one, directly connected. You can see in this picture these C's, and up here it tells us that C means it's connected. Connected has something called an administrative distance of 0, which means it is the most trustworthy. The lower the administrative distance, the more trustworthy that route is to that router. So it's really a believable one because it knows it. It can see it, right? Seeing is believing. So it really totally believes it. So it has an administrative distance of 0. Now that doesn't show up here anywhere, but we'll get into administrative distances a little bit more later on when we get into reading routing tables. All right, so those are directly connected routes, and that's automated. It all just, as soon as the router sees a network, then it knows what's connected. Now in this picture, we have 2 routers. This router sees 2 directly connected networks. This one right here, the 192.168.2.0 network, and this one over here, the 192.168.1.0 network. And that's all this router knows. And it would have these 2 directly connected routes in its routing table. This one, R2 over here, would have these 2 directly connected routes in its routing table right here. I actually have one of these things on a packet tracer. It looks just like this. And I'm going to call up router number 1 here. And let's just type show IP route. And here's the routing table, and sure enough, you can see that it has 2 directly connected routes, the 1.0 network and the 2.0 network, because it can see 1.0 and 2.0. This one over here should only be able to see the 2.0 and the 3.0 network. Sure enough, the 2.0 and the C0 are directly connected. Now you may remember in an earlier lab, in fact this is right out of that lab, you were asked to ping from PC1 to PC2, and it failed. And there was a question, why did it fail? And the answer, we're learning the answer now this week. Well, this PC sent the packet over to the switch. That sent the packet over to the router. Right now, the packet says, I want to send this to 192.168.3.10. And this router got a hold of that and said, 3.10? I don't know where 3.10 is. I can't see a 3.10. Well, of course it can't. All it knows about is 1 and 2. So it can't see the 3 network. So it rejected the packet and it didn't go anywhere. Now, here's an interesting question. Could I ping this interface, 192.168.2.1? And the answer is yes, I certainly could ping the 2.1 interface. Let's try it. Ping 192.168. What did I say? 2.1. Oh, sure enough, that's successful. Well, now let's see if I can ping the 2.2 interface. oh, this does not seem to be successful. Now, the question would be, why would this not be successful? After all, if this packet, destined for 2.2, came to here, and then came to here, well, this router knows about 2, right? So wouldn't it have sent it to here? Yes, it would have. And so this router now has the packet. So it did reach the router. However, this router here does not have in its routing table how to get back to 1.0. It says, hey, I know about 2 and I know about 3, but I don't know about 1. I have no idea where 1 is. And so it drops the packet at that point. So I cannot ping this interface. I can't ping this interface. I can't ping this interface. That's why that happens. All right, let's go back here now, and let's talk about static routes. So static routes are those routes that have been manually typed into a router. We'll demonstrate this in another video because it's going to get a little long on this one. But a static route is right here, and it shows with an S, and it has an administrative distance of 1. It's not quite as reliable as directly connected. The router almost believes it, but after all, the router says, that was a human that typed it in, and I don't trust humans nearly as much as I trust myself. And so it's almost a static, almost an administrative distance of 0, but not quite. So it would believe a route that was directly connected over one that was typed in. Finally, we have dynamic routes. Now, there are lots of different routing protocols, and RIP is one of them that we'll look at. We'll also look at EIGRP, and we'll also look at OSPF. We'll look briefly at them because there's a lot to learn about them, so we won't get that deep. This is an example of a route that was learned through RIP, and you can see it has the R over here. Now, these administrative distances depend on the routing protocol. So you can see that RIP here is not as reliable as OSPF, and OSPF is not as reliable as something called internal EIGRP. So it all depends on which routing protocol. Now, in this case, we actually have it right here. This is the administrative distance, and it says 120. So it tells us the administrative distance here is 120. Now, there's another number here that we will get into later on, a 1 that's after that, but we'll talk about that in another video. I'm going to cut this one off now, and in the next video, I'm going to demonstrate static routes.